You probably recognize this situation. You think you found the best motor for your application, but just before you finalize your design, you discover, oh my god, my motor doesn't have a datasheet. Well, in this video, we discuss how you can determine the most important motor parameters by using a practical approach. And we are going to do that by using three equations which are valid for a DC motor, which is the motor voltage relation, the motor voltage equation over here, the motor current relation between torque and current, which is over here, and the motor torque equation, which is over here. Let's start off with the motor voltage equation. Remember, it says the motor voltage U equals the back EMF, K times omega, so the motor constant times the radial speed of the motor, plus R times I, which is the motor resistance times the motor current, plus L times the IDT, the inductance multiplied with the change of the motor current. Then we have the relationship between current and torque, which says that the motor current equals the motor torque divided by the motor constant K. And the motor torque equation says that the motor torque is equal to J, the inertia, times d omega dt, the angular acceleration, plus the damping times omega, plus the friction torque, TFR. Three equations, and from these three equations we can determine the most important parameters: K, the motor constant, the R, the motor resistance, and the J, which is the motor inertia. So these three motor parameters are the most important one for doing your design. And then we have left for some specific applications the motor L, motor inductance, the D, which is the damping of the motor, and the friction of the motor, TFR. So we can do that also by using doing some tests and using some equations. Well, let's start off determining the K and the R. And there are two situations or two methods in which we can determine that K, the motor constant, and the R. And the first way of doing it is looking to the static motor voltage equation. And we apply that motor voltage equation in two situations. And these are two load situations, and in that way we have two equations and two unknown values. So how does it work? We measure in two load situations, and at a constant motor voltage, the motor current in amps with an ammeter, and the motor speed in RPM. And you can do that by using an encoder plus a frequency meter, or when your motor doesn't have an encoder, you can use a contactless tachometer. Okay, which load situation can you use? Well, the most easy one is the no load situation, and then you pick another one, another situation in which you load the motor with a specific load. It doesn't matter what kind of a load, as long as the motor load is constant. So we then apply these situations to the motor voltage equation. So we solve twice this equation. U equals K times omega 1. So it's N1 divided by 60 multiplied with 2P. Remember, we measured the speed N over here. So N divided by 60 times 2P plus R times the current in the first situation, so in the no load situation. We use again the motor voltage equation for the second measurement, in which this is omega 2. So it's N2 divided by 60 times 2P, and we have the current in the second situation over here. So we have two equations, and we have two unknown values, the K and the R, so this yields the K and the R. Okay, there is another way for determining the K and the R, and in that way we first define the R, and then we are going to determine the K. The determination of R can be done in this way by locking the motor voltage, by locking the motor and applying a low motor voltage to that motor. And we then measure the motor current, and by applying Ohm's law, we can calculate the motor resistance R, which equals U, the voltage, over I, the current. Remember, the motor voltage has to be low, because when the motor voltage is too high, the dissipation in the motor will be too high and the motor heats up and the R changes over time. So apply a really low motor voltage. Um, how can we determine the K? Well, we apply a motor voltage to the motor. We measure again, like in the previous measurement method, we measure the speed of the motor and the motor current, and we calculate the motor constant K by using the motor voltage equation. Remember, in this situation, the R is already known. So then we can calculate the K. We can determine the K also in another way by using backspinning. And then by using backspinning, you drive the motor by another motor and you measure the motor speed and you measure the motor back EMF by measuring the voltage at the motor terminals. And the motor voltage at the terminals equals the back EMF. And remember, the back EMF is K times omega. So when we measure the speed, then we can calculate the K by dividing the back EMF over the omega, and the omega was equal to n over 60 times 2p. So also backspinning can be done for determination of the motor constant K. So well, now we have the R and we have the K. What's left is the motor inertia. Oh, one remark, don't use a multimeter for determining the resistance, because a multimeter gives a too low motor current and that doesn't yield a very valid measurement result. Okay, now let's look to the determination of the inertia J. What we're going to do is we apply a step wave voltage to an unloaded motor. And then the motor speed increases according to the E-power curve. And this picture shows what happens. So we apply a motor voltage, in this example 24 volt, to the motor, and the motor speed increases through this curve, E-power. And according to this equation, we can say that the motor speed at every point in time equals the end value of the motor speed, the angular velocity over here, times 1 minus e to the power minus t over tau. And tau m, is the motor time constant. How do you measure the speed? Well, you can do it either by using an encoder on the motor shaft and use data logging in MATLAB Simulink, or you can do it by using a frequency to voltage converter and put the output of that FV converter, for instance, on a socket, to an oscilloscope. Okay, so now we have the motor speed, and then we can determine the time constant of the motor. And the time constant of the motor equals the motor inertia J times R, which is the motor resistance, divided by K squared, so the motor constant squared. And remember, the K and R are already known, so when we measure or can determine the tau, we can calculate the J, the inertia. Well, how do we measure that time constant tau m, the constant time constant of the motor? We do it by looking to the 63 percentage point of the motor speed. So the point where the motor speed reaches 63% of its end value. And the time, which equals the 63% end value of the speed, that time related to the start time, so related to, in this way, almost 0 seconds, that difference is the motor time constant, tau m. So again, by looking to the 63% value of the motor speed, we can look to the time, and the time difference between that time and the starting time equals the time constant tau m over here. So now we have tau m, we have R, we have K, and we can calculate the motor inertia J. Alright, 3 parameters left. So let's look how we can determine the inductance of the motor L. And we do that by using, again, a step response method. We lock the motor and apply a low step voltage again to the motor. And again, it has to be low so we have to avoid dissipation in the motor. And now we are going to measure the motor current, and we do that by using an inductive current probe and connect that current probe to an oscilloscope, and we get a current wave on that oscilloscope. And again, we are now looking to the 63 percentage point of the current with respect to its end value. And at that 63% point of the current, we can measure the time, and that equals the time constant tau. Remember, it has to be relative to the step time where the current starts rising. So it's more or less similar to determining the mechanical time constant, tau m, but now we have to look to the motor current, which yields the electrical time constant of the motor, tau e. And we now can calculate the motor inductance by applying this equation. Tau E equals the inductance of the motor divided by the motor resistance over here. So we measured the tau E, we knew already the R, and we can calculate the L. Another thing which you can do is use an LCR meter, if of course available. Okay, last two parameters are the damping and the friction of the motor. What we do in this situation, we connect the motor to a variable voltage source or power supply, and we place in between the motor and the voltage source an amp meter. Could be a standard amp meter. And now we measure at different voltages, doesn't matter what voltages, but at different voltages we measure the motor current with the amp meter, and we are going to measure the motor speed again by using the encoder data with frequency meter, or we are going to use a contactless tachometer. Now we measure in every point, or we calculate in every measurement point, the motor torque by multiplying the measured current by the motor constant K, and we calculate the motor speed omega by either using the frequency of the motor, and then we have to divide the frequency of the encoder by the end of the encoder, and the end of the encoder are the number of pulses per revolution, and multiply that by 2p. So frequency of the encoder divided by the number of pulses per revolution multiplied with 2p. But when you use the tachometer, you probably measure the motor speed in RPM, and then you have to use that RPM, divide that by 60, and multiply it again by 2p. So now we have the motor torque, and we have the motor speed omega. Next, we're going to plot these measurement points in a graph, and on the horizontal axis we place the omega, and on the vertical axis we place the motor torque Tm. And we draw the internal load characteristic by drawing a straight line or a trend line through the measurement points. So I did that over here. These are my measurement points, and here Excel has drawn a trend line over here. And by means of this characteristic, we can determine the friction and the damping. The friction, TFR, is the intersection point with the y-axis, so over here, this point. So at omega is 0. So in this example, my friction torque is 0.012 Newton meter, or 1.2 Newton centimeter. The motor damping is the slope of this line. So it's delta T motor divided by delta omega of the motor. So it's this slope, and in this example is 1 times 10 to the power minus 5 Newton meters per radians per second. So, well, that's all summarized. We discussed some ways to determine the most important motor parameters. So the last thing I can do is wishing you good luck with your motor design, and thank you again for watching. Bye bye.